It's the night of July 9th, 1962. On a small atoll in the Marshall Islands, the sky is clear, except for a thick band of clouds on the horizon. Suddenly, the eastern horizon lights up, but it's not sunrise. A white flash burns through the dense clouds, and from that flash grows a vast sphere of green light. Nebulous white filaments leap from the bowl and arch across the sky before fading as a chain of circular shock waves erupt from the side of the flash. It's over in less than a minute. But then a dull burning red glow grows across the eastern sky, cut with enormous white rainbows, and lasts for an hour and a half. If there was anyone from the Arctic present on that near equatorial island, they may have recognized the telltale patterns of aurora dancing in the sky. But this was no natural aurora. It was the result of a thermonuclear detonation in outer space, 400 kilometers above another small atoll, 1,400 kilometers distant to the east. This was the Starfish Prime test, and its unexpected devastation helped usher in an era of nuclear peace, an era that may or may not persist. Starship Prime was the largest of the 5 thermonuclear tests that the United States conducted in space. There was a Big Bang, and there was radioactive fallout, which is its own troublesome tale. But today we're telling the story of the 10 to the power of 29 electrons that were produced in the explosion or released as gamma rays to ionize the upper atmosphere. These particles spiraled along the Earth's magnetic field lines, causing those artificial auroras I described, but also leading to the creation of a new radiation belt, several orders of magnitude stronger than the Earth's natural belts, and they lingered for 5 years. A third of all low Earth satellites were destroyed due to repeated passage through this belt. Admittedly, at that time, a third of LEO satellites was 6 satellites, but today that would be thousands. And right after the explosion, a cascade of ionization caused an electromagnetic pulse, an EMP, that disrupted electronics over much of the Pacific Ocean. In Honolulu, 900 kilometers from the blast, hundreds of streetlights just went dark. Starfish Prime was a devastatingly clear demonstration of the destructive power of nuclear weapons in space. Clear enough that in 1963, the world's main nuclear powers ratified the Partial Nuclear Test Ban Treaty, banning space and under-ocean nuclear testing. This was followed in 1967 with the Outer Space Treaty, a broad agreement for the peaceful use of space, and which clearly bans any nuclear or other weapons of mass destruction being used or staged in space. But treaties are only as good as far as we obey them. In early February, there were media reports that US intelligence had evidence that Russia is developing a new space-based military nuclear capability. There was frustratingly little detail. We don't even know what type of facility this might be. But various pundits have speculated that it could be about developing the capacity to perform EMP attacks, either an actual EMP generating satellite or the capability for detonating nuclear explosions in orbit, similar to Starfish. This episode isn't about what Russia or any other nation may or may not be doing, but in light of the media rumour mill, it seems like a good time to bring science to one aspect of this issue. What would happen if we nuke space? What would happen if a Starfish Prime-like event happened today? Let's start with what's probably the best known effect of nuking space, the electromagnetic pulse, the EMP, because that's the main direct effect on the ground. EMPs are all over science fiction. They're great for when you want to shut down a spaceship without destroying it. They're also a handy way to obliterate modern technology to kickstart your post-apocalyptic drama. But EMPs aren't science fiction. Real militaries are experimenting on real EMP generators, and as Starfish Prime showed us, space nukes can send powerful EMPs to the surface. So what exactly is an EMP, and how dangerous are they? Let's start with the EM part of EMP. An EM wave, an electromagnetic wave, is a self-propagating ripple of electric and magnetic field caused when charged particles accelerate. EM waves travel at the speed of light because light is an EM wave. When such a wave encounters another charged particle, those rippling electric and magnetic fields cause that particle to jiggle, effectively transferring energy and information between two locations. The wavelength of the wave determines the scale of the jiggling. Microscopic wavelengths jiggle things on the scale of atoms. For example, electrons jumping between atomic energy levels in your computer screen creates EM waves several hundred nanometers in wavelength, just the right wavelength, needed to jiggle electrons in your retina. This is visible light. But a current bouncing up and down on a distant antenna creates an EM wave from centimeters to meters in wavelength, radio waves. And these cause electrons in your, say, cell phone's antenna to jiggle in unison. So what about an EM pulse? These are very short, very intense bursts of radio wavelength EM waves. They cause electrons to jiggle in wires just like any radio signal. The difference here is that the intensity is so strong that it causes a lot of electrons to move, potentially sending high currents through wires or even circuitry. Generating excess current in, say, computer circuitry will at best cause the computer to shut down. But current also causes heat, and heat melts wire. A large EM pulse will fry electronics. Generating too much excess current in a national power grid will melt transformer coils and shut down the grid. To make an artificial EMP, you basically need to apply an extremely high voltage across a conducting coil. The energy requirement typically means you can only do this for a very short time. Now, the simplest EMP device would consist of a bank of capacitors connected to a high voltage power source and multiple loops of wire, with the circuit broken by a spark gap. Charge will build up in the capacitors until there's sufficient voltage for the air between the charge gap to ionize and close the circuit. All those stored electrons will suddenly flow through the loops, generating an enormous magnetic field that kickstarts your EMP. It seems like you need a pretty specific set of conditions to generate an EMP, and so it seems surprising that a giant explosion in the sky produces an EMP by basically the same mechanism. Where does the electrical current come from? Why is it moving in circles? And how does the resulting electromagnetic radiation pile up into such a sharp pulse? Let's start by remembering how nukes work. In general, we're talking about modern thermonuclear bombs here. These work by compressing a bunch of hydrogen to such a high density that it mimics the processes in the hearts of stars. Hydrogen fuses into helium and releases an enormous amount of energy in the process. A small fraction of this energy is released in the form of a very rapid burst of gamma rays, the highest energy electromagnetic radiation. None of that radiation makes it to the ground, thankfully. To gamma rays and also to X-rays, Earth's atmosphere is basically opaque. They can travel very little distance before bumping into some air molecule. But although the actual gamma ray photons don't make it to the ground, some of their energy does. When a gamma ray hits a molecule, it typically scatters off an electron. The energy of gamma rays is so extreme that the electron is knocked free out of its atom and sent hurtling downwards at roughly the same direction as the gamma ray, which itself continues on but with reduced energy. Now, that fast-moving electron finds itself in the presence of Earth's magnetic field, Earth's geomagnetic field. Magnetic fields exert a force on moving charges, and this charge is moving fast. The electron begins to spiral around the geomagnetic field lines. Now, remember how we made our artificial EMP by sending a huge current around a loop? Well, here's a current moving in a loop. The spiraling electron creates a minuscule EMP that travels in the same direction as the original gamma ray. This doesn't sound too dangerous yet, but remember that the EMP travels at the speed of light, the same speed as the gamma ray that created it. It keeps up with that photon, and so further scattering events will add to the strength of this one narrow pulse. In fact, as the entire thin shell of gamma rays passes through the atmosphere, it gets converted one scattering event at a time into an increasingly powerful electromagnetic pulse that always keeps pace with the fading gamma ray shell. By the time the shell is gone, the pulse is powerful enough to do its damage. The potency and range of such an EMP depends on the size of the explosion and the altitude. In general, any explosion from orbit will affect a continent-scale region, ultimately limited by the curvature of the Earth. The 400-kilometre high Starfish Prime explosion blew out transformers 1,400 kilometres away in Hawaii. It's estimated that a similar thermonuclear explosion above a large populated landmass would cause massive currents in the electrical cables that crisscross the continent, burning out hundreds of the insufficiently protected transformers connecting that network. This would result in blackouts across that continent, and it could take years to repair. The effect would be similar to us getting a direct hit from a major coronal mass ejection from the sun, a blast from a solar magnetic storm like the one that smacked us back in 1859 before we had an electrical grid to worry about, or that blacked out all of Quebec in 1989. Probably we should put more of the relatively cheap safeguards in place to avoid the multi-trillion-dollar cost of repair after an electromagnetic incident, whether natural or otherwise. So, space nukes can make a mess on the ground. They're also not very good for space. I told you that the Starfish Prime test wiped out low Earth orbit satellites. Let's see exactly how that happened. The EMP we just talked about is generated by electrons spiraling along Earth's magnetic field lines. Those electrons don't go away after generating the pulse. As they get closer to the ground near the poles, the changing angle of the field lines means that the pitch of their loops relative to those field lines change. When the pitch is inverted, the magnetic force on those electrons pushes them in the opposite direction. They're reflected before they reach the ground, and they start traveling back up the field. This happens again when they reach the opposite end of the field on the opposite hemisphere. In this way, an electron can bounce back and forth until getting absorbed by the atmosphere or being knocked free by a solar photon. But until most of the electrons are so liberated, they remain bound in this band that traces the geomagnetic field. At the same time, east-west smearing of the electrons causes the band to form a toroidal belt around the whole Earth, a radiation belt. Earth has two natural radiation belts, the Van Allen belts, discovered in 1958, only a few years before the Starfish Prime test. These are also made of charged particles bouncing along our geomagnetic field lines, but here they're mostly high-energy electrons and protons from the solar wind, with some cosmic rays for good measure. They extend from around a couple of thousand to 60,000 kilometers above the Earth, with a gap between them at around 2 to 4 Earth radii. We do not put satellites in the Van Allen belts because those satellites' electronics would degrade pretty quickly. We're lucky that geosynchronous orbits are in the safe zone between these belts. Low Earth orbit satellites are also safe if they stay below the inner belt, below around 2,000 kilometers. And these days, that part of space is pretty densely packed with something like 5,000 satellites. So you can imagine the problem if a Starfish Prime-like event happened today. A space nuke can target a very specific, if very large, region on the ground with an EMP, but it's indiscriminate in its damage to satellites. Low Earth orbit would gain a charged particle density similar to the Van Allen belts, perhaps wiping out a good fraction of satellites there. Hopefully this is a strong enough deterrent against such an attack by a nation that's also dependent on those satellites, which includes most nations capable of launching such an attack. There are ways to harden satellites against increased charged particle flux of a new Starfish Prime-like event, but that's expensive. The United States is moving more in the direction of redundancy, having just launched a prototype to test its proliferated warfighter space architecture. And this program aims to blanket low Earth orbit with hundreds of small Starlink-like satellites. The philosophy is that it's harder to wipe out many small cheap satellites, whether with an artificial radiation belt or a targeted EMP, and they're also easier and quicker to replace. The effects of the Starfish Prime test were far more widespread and damaging than anyone expected. But the silver lining to this mushroom cloud is that the world came together to first ban the most irresponsible nuclear tests, and then to commit to the peaceful use of space with the Outer Space Treaty. But good intentions don't last forever. Given the global existential threat of putting nukes in space, we should choose our path carefully. Do we want to move into a new era of militarized space? Or do we reaffirm our commitment to our 60-year-long peaceful space time.